Hey guys, today we are going to be going into sampling distributions, and this is the start of basically the most important unit in statistics, and it's also where things get really applicable to real life. So a quick introduction for what kind of scenarios you'll see sampling distributions in. There's two main ways. One is for proportions and one is for means. So let's say 40% of a college is in favor of putting more vending machines on campus. If we randomly choose 10 people out of everyone in the college and find what proportion out of those 10 people are in favor of the vending machines, what number will we get? So if we choose 10 people out of the entire college to give their opinion on the vending machines, we already know that 40% of the actual student body is in favor of the vending machines, but that doesn't guarantee that 40% out of the 10 people will be in favor of the vending machines. So you already know right away that the proportion is going to vary from sample to sample, and this is a really important thing to keep in mind. Although the population center of the proportion of people in favor of the vending machines is 40%, what we actually get from samples is going to fall around 40, but it's going to vary between samples. So that's for proportions. For means, we have a similar situation. If the average GPA in a school is a 3.2, what numbers would we get if we took 10 students at a time and averaged their GPAs? So even if we take 10 students and then get their GPAs, these could be 10 really smart students, and we could end up with a really high average GPA in that sample. So again, the average GPA is going to vary from sample to sample. However, logically, it's still going to fall around 3.2 because that is the population center. The main concept here I'll show you in a moment. And Rice University actually has this amazing online applet that gives a visualization of this concept. So before I get into how it actually works, there's a couple things that you need to know on how to read this. So this thing right here tells you what kind of distribution the actual parent population has. The GPAs in a school could be normally distributed. That means it falls around a center value and is unimodal and symmetric. Or the school GPAs could be uniform. So there's the same number of people in each GPA value. Maybe 10 people have a 2.0, 10 people have a 2.1, 10 people have a 2.2, all the way up for all the GPA values. And then a skewed distribution is if, let's say, a lot of the people in the school have low GPAs, but there's still people to the really high end that are pulling the average GPA upwards. So we're going to work with the normal distribution first, the normal parent distribution. You will see the parent population is normal, and then we chose a sample of, I chose 5 out of our parent population. So I sampled 5 people out of that school, and I averaged their GPAs, and their GPA ended up right here. One more thing you should note is that this little red thing right here, the line going outwards is marking the mean. So your mean value is around here. So we sampled 5 people and we got a sample average that came out around here. It's not equal to the mean, but it's around there. And so I kept taking samples and samples. I took 30 more groups of 5. And then as we sampled more and more, we got more, and they started to show somewhat of a pattern. So we can see somewhat of a unimodal distribution occurring. And as we do that more and more, I think I took it about 100,000 more times using this button here, we have gotten what looks like a normal distribution. So this is always going to be true. Whenever you keep taking samples out of this parent population, we will eventually get a normal distribution in terms of the sample averages. So let's actually go and do that now, just for a better visualization. So here's our normal model. We're going to take 5 out of the population. We took 5 people. There's their average. Here's the population average. Let's take another 5. That one falls around there again. And we have our sample mean emerging over here as well. That is our pink line. Note that it's not the same as our parent population line, but it's close. Again, we have another one. Let's take 5 more. And you'll see that we're starting to get more and more values around this parent population's mean. So if we keep doing that, you can see it's starting to turn symmetric. I'll do the shortcut, I'll take 10,000. And we note that this is a very symmetric, very nice normal model. So generalizing that, what happens when we have a uniform distribution for our parent model, or a skewed distribution? And here I just randomly ran my finger across the screen and I had this distribution. For all of these, no matter what, as I kept taking samples, the samples still end up making a normal distribution around our population mean. No matter what our population looks like, our sample distribution is still going to look like this. And that is what a sample distribution is, and that is our blue distribution here. Our blue distribution is the shape that we get, the graph that we get when we keep taking samples out of our population. So as we took sample after sample out of this parent population, our means eventually turned into something like this. Our average values turned into something like this. So if you don't believe me, we can do that now. So let's take a uniform distribution. Taking 5 at a time, we can see that even though there's an equal chance of getting every value here, because there's an equal number of things in each category, we're still likely to get something around the center, because if we get some really, really low value here, it's going to be dragged upwards by values that we get from out here. So they're going to pull values towards the center. So if we keep taking values, you can see we're starting to get a sort of clustering around the middle. Taking 10,000 more, there is our normal model. Next is skewed. Even if it's skewed, we're still going to get a normal thing. So going again, so if we keep doing that, we can see our distribution start to take form. And there we go. And the big rule here is just that no matter what distribution we choose, what distribution our parent looks like, it's still always going to be a normal distribution. And that is the central limit theorem. What this central limit theorem is like the central pillar of this unit, and you'll use it so much in the coming videos. So what it says is, no matter what the population looks like, if you keep taking samples from it and averaging the responses will form a normal model. This is going to work for proportions and for means. So the means is basically what we just did. We took 5 people out of the population, and then we took their average whatever characteristic. For proportions, it's a little bit tweaked, but it's basically the same concept. So if 40% of the college campus is in favor of the new vending machines, and then we take 50 people out and sample them about whether they're in favor of it, if we keep doing that over and over again, we will get a distribution that's centered around 40%. The sampling distribution is the distribution that we get when we take samples out of the population, and that would be all of the normal models that we just saw. You'll note that for each of these normal models, each of them has a mean and a standard deviation. So coming up here, we're now going to start finding what these means and the standard deviations for these normal models are. Even if our parent model is normal, so this one, the parent has its own mean and standard deviation, but you'll notice that our sampling distribution, our blue one, this is a different model. These two models are not the same. If you'll note, you'll see that this model right here is way more skinny than our parent model, so that makes our standard deviation, at least, very different from that of the parent population's model. So you need to keep that in mind, that the parent population, the parent parameters such as their mean and standard deviation, is not necessarily equal to the sampling distribution's mean and standard deviation. And there's a way to calculate each of those. For our proportions, your mean stays the same. Your mean will be equal to some p-value. So that is your p for what proportion of people have this trait, what proportion of the population supports this opinion. So if 40% of our college is in support of the new vending machines, then our p is equal to 0.4. Our standard deviation will be equal to the square root of p times q over n. This is only for when we're working with proportions. So our proportions are whenever we see our percent and our fractions. So 15 out of 900 people support whatever political party. That is a proportion. So means is when you're actually taking the raw values and you're taking their average value. So for your mean value stays the same, but instead of a p, we have mu. So mu will be your population mean. And then your standard deviation of your sampling distribution will be equal to your population standard deviation over the square root of n. So this is where you really need to keep in mind your population standard deviation is not equal to your sampling distribution standard deviation. You actually have to tweak your population standard deviation to fit your sampling distribution, and that is what we do here. So we take sigma over the square root of n. So this is what these distributions look like. If you'll remember before, for our normal models, there was a special notation for these models where it was n for normal, and then we have our first term representing our mean, and our second term representing our standard deviation of this model. For a proportion, the mean will always be your population p. That is at the center of our model here. And then we branch out with our standard deviations. So our standard deviation is equal to p times q over n, and then we take the big square root of that. If we go out one standard deviation, we have p plus qn and then p minus qn, two standard deviations, p plus 2 times square root of pq over n, etc. You might remember that there is this thing called the empirical rule for normal models. So it says that 68% of the data is within one standard deviation, 95% of the data is within 2 standard deviations, and 99.7% of the data is within 3 standard deviations. That still applies here. So if we put out our fences here, so we have marked out our 1 standard deviation line. That means that yes, 68% of the data is within these 2 lines. We can do that for 2 standard deviations and 3 standard deviations as well. This is a really important concept that you will use for almost all of your calculations from now on. Your distribution for your mean is also very similar. So we have, again, our normal model notation here, n of mu for population mean, and then your sigma over your square root of n for your sampling distribution's standard deviation. It's a lot of vocabulary, I know. So here's our center, again that's mu, and then plus 1 sigma over square root n, plus 2 sigma over square root n, So we have our mu here, and then that would put 68% of the data between these 2 lines. There are certain conditions that we have to fulfill in order to use these models. So that's these 4 right here: independence, randomization, 10%, and large enough condition. You have seen some of these before, actually, whenever we were doing our binomial and geometric models, as well as when we were doing our simulations. Our independence condition says that one sample or subject should not affect another. So whether one person is in support of our vending machines should not affect if another person is in support of the vending machines. Or if we're talking about height, so the height of one person should not affect the height of another person. Next, we have randomization. So we have to ensure that our samples are randomly taken. For 10% condition, again, you have seen this before, we are sampling under 10% of the population to, again, ensure independence. Finally, we have our large enough condition. Our previous 3 are always going to be the same between proportions and means, but our large enough condition is going to change quite a bit between our means and proportions. So for proportions, again, our independence and randomization is the same, but our large enough condition comes in the form of a success-failure condition. So this is something that we have to expect. We have to expect 10 successes and 10 failures out of our sample. Putting this into math terms, you'll remember we have an n, p, and q, right? N is now no longer the number of trials, but the size of our sample, and our p is our population proportion. And what the success-failure condition says is that NP, the number of people in the sample, times P has to be greater than or equal to 10 because NP represents the number of successes. So P still represents the probability of success. For failures, that is NQ. So NQ also has to be greater than or equal to 10. NQ is representing number of failures and NP is representing number of successes. So we have some practice with the conditions here. The first thing you know about this problem is that it is about proportions. because over here you see a percent sign. In questions, as soon as you see a percent sign, or if the question is talking about some fraction of a population, you know immediately that the question is going to be about proportions, and you know which set of conditions to use. So the question says, 60% of a population has type O blood. I'm randomly taking 50 people out of the population at a time, and then looking at their blood types. So for independence, this is when one subject does not affect another. So does the blood type of one person affect another? We say no. Independence has been maintained. So we would write it like this. Next, we ask ourselves, is the sample randomly taken? So we go back to the question and we see in the second sentence this word right here, randomly. So yes, our sample is random. How would we write that? A random sample of the population was performed. Another thing that you can do is actually combine your independence and randomization conditions by saying that because we performed a random sample, the blood type of one person is independent of the blood type of another person. Because in taking a random sample, you're basically breaking the relationships between people. So now we have the 10% condition. So this one says that we have to sample under 10% of a population. Well, 50 people is our sample size, and 50 times 10 is 501. So that just means that our country population has to be over 500 people. That is very easily satisfied considering all the countries in the world right now and their current populations. So we say this. 50 people is surely less than 10% of all the people in the country. Note that I kind of use a shorthand here, just the less than 10% symbol. It really doesn't matter. It's up to you whether or not you actually write out less than 10% or use the math symbols, as long as you get your point across. Next is success failure. So this is the one that says our NP has to be greater than 10 and our NQ has to be greater than 10 or equal to 10. So first, what is our N, our P, and our Q? Because that is what we need to check with. So our N is our sample size. That is 50. Our P is the probability of success. So the probability that someone has type O blood. That is our 60% here, and that leaves 40% to not have type O blood, and that is our Q. Writing that out, that would look like this. Because NP is equal to, and then we plug in our important numbers, so N is 50 and then P is 0.6. Multiply those two together, we get 30, and that is greater than or equal to 10, and then NQ is equal to 50 times 0.4, which is equal to 20, and is also greater than or equal to 10. So the sample is large enough. And that is our original condition, because the success failure condition is just stemming off of the ultimate is the sample large enough question. So finally, now that we have satisfied all of our conditions, we need to conclude. So we just say we have satisfied the conditions, we can proceed with whatever we're going to do. In the future, this might be a t-test or a z-test. So there we go. Next, we have a different set of conditions for our questions about means. So this is when we're not talking about percents anymore, we're talking about actual numbers when we average raw data. So our independence, randomization, and 10% condition are still the same. It's just one subject does not affect another, the sample is randomly taken, and we sampled under 10% of the population. But our large enough condition is a little bit different now. It basically says that whether or not the sample is large enough is completely dependent on N. So there's 3 different ways that this could split. The first is that if the sample is greater than 30, we're good. We can just move ahead with everything. We don't have to worry about anything else. So if N is greater than 30, that's fine. Nothing matters. You can just go ahead. The sample is definitely large enough. If N is between 15 and 30, then we have to look at our sample. So does our sample have a sort of unimodal and symmetric distribution? So that means if we take that sample of 50 people, get their heights, and then put their heights in a histogram, does the histogram look unimodal and somewhat symmetric? So this one, you do have to look at a histogram or some kind of plot of your sample, but as long as it basically just has one mode and then no outliers, then you're basically good. Symmetry is really, really flexible here. And finally, if N is less than 15, your parent population must be normal. So that means when you take your sample, your parent population shape actually matters. So when will the parent population be normal? This is something that the problem will either tell you or you'll have to infer on your own. In cases where you have to infer on your own, there's one main principle that you should always keep in mind. and it's that natural phenomena is almost always normal. So the heights of people in a country, that is usually a normal distribution. The same with weights, and then like cat length or something like that. So we have another question now. The average height of the seniors in a high school is 168 centimeters. I randomly select 50 students at a time and record their average height. So first we have our independence condition. So will one student's height affect another one's? No. And then if we want to put those together with the randomization condition, well, we see the word randomly over here, so we already know it's random. So let's put these two into one sentence, and that would look like this. Because the sample was randomly selected, the height of one student should not affect the height of another. Note that I'm using the words student and height, so that is our question context, and that is really, really good to include. If you just put words like the height of one subject should not affect the height of another, that works, but context is always the more the better. Now we have our 10% condition. So is 50 students less than 10% of all of the high school seniors? Personally, in my high school, it's a big high school, there's about 1,000 kids per grade, then 50 students is definitely less than 10% of all of the seniors. Using that assumption, we'll just go ahead with that. 50 students is surely less than 10% of all students in 12th grade. And now we have our large enough condition. So this is when we look at the sample size. So we have 50 students, and our large enough condition said that if we have more than 50 people in our sample, then we can just go ahead. We don't need to check anything else. So we say this. Because n is equal to 50, which is greater than 30, the sample is large enough, short and sweet. And finally, we just need to conclude. This is my basic template of conditions for both proportions and means. And this one, it's not really a matter of how well you write as long as you get the content down. So if you're not familiar with anything, follow my format. Some quick practice with the actual math. If the mean weight for all of the employees of a company is 140.74 pounds with a standard deviation of 51.54 pounds, what is the mean and standard deviation of the sampling distributions of the means for the company? So there's three main steps you should always follow. The first one is identify whether this question is about means or proportions. So the main thing that will tip you off that this question is about means is your numbers here, 140.74 and 51.54. For proportions, your numbers will always stay between 0 and 1 or between 0 and 100 if we're talking about percentages. So that makes this one definitely a question about means. So now that we know that this question is about means, we know which formulas to use. So step 2, identify the important numbers. So the numbers we need here are a population mean and a population standard deviation. So we can write those down now. Our population mean is the mean weight of the company. So mu is equal to 140.74 pounds. And then our sigma, so our population standard deviation, not our sampling distribution standard deviation, is equal to 51.54 pounds. And then step 3, make the needed adjustments. So you'll remember, for means, your population mean will be the same. So this one does not get any adjustments made to it. But our new standard error or standard deviation of our sampling distribution will change. So let's say we are taking sample sizes of 50. Sample size 50. So we're taking 50 employees out at a time and we're averaging their weights. That would be equal to our sigma over square root of n. So that is equal to sigma of 51.54 over the square root of 50, which is our sample size. And that is equal to 7.28886 according to Siri. So that means that if we take samples of 50 at a time, then we will have a normal distribution with a mean of 140.74 and a standard deviation of 7.28886. You'll note that our standard deviation is much smaller than our sigma, and this is because we have a large sample size. It makes sense to think that the larger sample size you take, the less variation you'll get. Your individual will vary more than your mean, and your individual standard deviation will vary more than if you take giant groups at a time. Extreme outliers tend to get counteracted by the weight of other people. No pun intended. So a second practice, if 36% of a company's employees weigh over 140 pounds, what is the mean and standard deviation of the sampling distribution of proportions? So you see the word proportions, you see the percent, you know that this question is about proportions. Next, what are our important numbers? So again, let's say we're taking a sample size of 50. I apologize for not including that before. So what are our important numbers? For proportions, we need a P, so probability of success, a probability of failure, and a sample size. So a P, a Q, and an N. P, Q, N. Our P seems to be the probability that someone weighs over 140 pounds. So that is our 0.36. Our Q is 1 minus 0.36, so 0.64. And our sample size is 50. That is step 2. Step 3, again, make the needed adjustments. So our P stays the same. Our population center stays the same. And our standard error, though, that one changes. So our standard error is equal to square root of PQ over N. So you'll note a big difference here between proportions and means is that for questions about means, they will give you a standard deviation. For a question about proportions, they will not. So our standard error will be equal to the square root of P times Q over N. Putting that into the calculator, we get 0.0679. So our standard error is about 6.79%. Because again, this can all be expressed as percentages. Our P could be 36% and our standard error could be 6.79%. It's all up to personal preference. I just prefer it as decimals. So there are full free response questions about this. That is really when we start to go into the real stats and the real probability. So here are the main steps for it. Your first step will always be to list out your conditions. And then your second step will be important numbers. These two can actually be interchanged. I usually put the second step first, but some people like to see the conditions first. And then these two should definitely be switched, my bad. But first, you get a z-score. If you don't remember how these work, you can go back to my chapter 5 video on how normal models work and what z-scores are. And then once you get your z-score, you will draw out your normal model and you will mark where your z-score is. So if you get a z-score of 1, then you would draw your normal model, you mark your 0, you mark your 1, and you say this is where my z-score is. And then you will find the probability. So you'll find the probability that your z-score or above happens. You'll see what I mean in a minute, and then you'll conclude based off of this probability. So what does that probability mean for us? So here's a question. This is for proportions. Suppose that about 13% of the population, let's say that's the entire world, is left-handed. Again, I don't know the numbers. This is straight off of the textbook. A 200-seat lecture hall has 15 lefty seats, so these are the seats that have the built-in desk on the left rather than the right. And in a class of 90 students, what is the probability that there will not be enough seats for the left-handed students? I skipped the first step because that would take a lot of writing, but let's just say we already finished the conditions, and this is good practice for you if you want a review on how to do this. I will put a full answer up in the description box. So we just list out our important numbers now. So our important numbers, we need a P, a Q, and an N. So our P is 0.13. So we're modeling the population's left-handed group of people. We say 0.13 as the proportion of people that are left-handed. Our Q is 0.87, so everyone that is not left-handed. And then N, so that is the size of the sample that we're taking. That is here. So our class is our sample now. So in a class of 90 students, what's the probability, blah, blah, blah. So our sample size is 90, because we're looking at 90 students. And we want to know the probability that there will not be enough seats for the left-handed students. Now that we have our important numbers, we can actually solve this problem. So you'll remember that we need to calculate our z-score next. The formula for a z-score is equal to our sample minus our population mean over our standard deviation or standard error, right? But we don't have a standard error right now, so that is what we need to go to first. So the standard error of p, not p hat, my bad. The standard error of p is equal to the square root of pq over n. So we have all of our numbers that we need. Writing that into the formula, that would be 0.13 times 0.87 over 90. This can be done easily with a calculator, and we get 0.0354. So in order to calculate our z-score, we need three important numbers: our sample statistic, our mean statistic, and then our standard error. So we just got our standard error, our mean, so our p here, that we have that is our 0.13. So the one thing that we're missing is our sample statistic. This is the number that we're going to be comparing to the 0.13 of the population that is left-handed. So our sample should be the proportion of people in the class that are left-handed. What we're trying to find here is the tipping point when there's too many students for the lefty seats. So that means when all 50 lefty seats are taken up, that is our tipping point, because that is the point where we have run out of lefty seats. So this is the place that we have to calculate a z-score for, because once we get that z-score, we know that anything below that score means that we have enough seats for left-handed people, and anything above that score means that we do not have enough seats for left-handed people. That means our sample statistic must be that tipping point. Our class size is 90 students, and if 15 of those students are left-handed, that means if we add one more left-handed person, we will not have enough seats for the left-handed people. So that is going to be our tipping point, when we have 15 out of 90 of our students being left-handed. So we have to change that into a proportion now. So putting in 15 over 90 as our tipping point, our proportion ends up being 0.166667. Now that we can plug everything in, our z-score looks like this. We take our 0.16667 minus our mean proportion of 0.13 and then divide by our standard error. When I see mean proportion, that just means the population parameter, so the actual population proportion that is left-handed. Mean is just kind of a population center. Putting that all into the calculator, we get a z-score of 1.0358. So now we need to know how this relates to the normal model. Drawing it out, we get something like this. Here's our normal model, and we have flagged our 1.0358. So that is our tipping point. That means if the proportion of left-handed people goes any higher, we won't have enough seats for them. So that is all of the area up here. This is what we're interested in, and this is what we're going to calculate. So next we have to put this all into calculator language. So we want to know the probability that our z-score goes above this tipping point and goes into this area. So probability that z is greater than 1.0358. We need to put this in as a calculator function, and you'll remember that there is a function called norm CDF. Norm CDF, and our parameters are a lower bound, an upper bound, a mu, and a sigma. So our lower bound here is whatever's cutting off the beginning of our area. In this case, that is 1.0358. And we want to know the area from here to infinity. So our upper bound is just going to be infinity. Our mu is the mean of the standard normal model. So that is 0. And this should be sigma, my bad. Our sigma, standard deviation, is equal to 1. Putting that into the calculator, we get 0.15015. So that means there is a 15.015 chance that there will not be enough lefty seats for left-handed students. And that is our conclusion. There's a 15.015 chance that there's not enough lefty seats, etc. Last question, I promise. I know this is a long unit, it's a big concept. So the CDC reports that the mean weight of adult men in the United States is 190 pounds with a standard deviation of 59 pounds. An elevator in a building has a weight limit of 2,500 pounds. What's the probability that if 10 men get on, they will overload the weight limit? So first we have to find our population parameters. So this is what we got from the CDC, our summer statistics of adult male weight. So our mu is whatever the CDC said the mean weight was, 190 pounds, with a sigma of 59 pounds. And then our sample size is however many men are looking to get onto the elevator. So that would be 10 as the question asked. Now we have to go find our z-score. So again, we need that standard error. So we know that we need to adjust our sigma to get our standard error. So our standard error is equal to sigma over the square root of n, which is equal to 59 over the square root of 10. Putting that into the calculator, we get 18.657. Now that we have our standard error, what else do we need to get for our z-score? We will note that our mu is for an individual male. So our mu is 190 pounds. We are talking about when the weight on the elevator goes over 2,500 pounds. So the number that we put into our z-score is not 2,500 for our sample, but instead it's how this 2,500 gets spread out between these 10 men. So for simplicity, we will say that if each male weighs 250 pounds, then 10 of them getting on will hit the limit of 2,500 pounds. So we can put our sample statistic as 250 minus 190 for our mean now over our standard error of 18.657. So our 250 is our sample statistic minus our population statistic of 190 over our standard error. So again, the 250 comes from when the weight gets spread out between the 10 men, because we want to know how the individual weights of the men will affect the overall weight on the elevator. So putting that into the calculator, our final z-score is 3.216. So again, we do our big z-score thing. We draw our normal model. So here's our 0, 1, 2, 3. Our z-score looks to be around here. We flag it. We shade in the area that we're interested in. Probability that their weights go above here, so 3.216. And then we put that into our probability notation. So P z is greater than 3.216 is equal to, pulling out our calculator functions, norm CDF of lower bound is equal to upper bound, mu, and then sigma. So our mu and sigma, again, since we're on a standard normal model, are 0 and 1. Our lower bound is 3.216, and our upper bound looks like it is infinity. So putting that into the calculator, we get 0.00065. So there is a 0.065% chance that if 10 men get on, they will overload the weight limit. So you can see here how incredibly applicable this unit is to real life, and that's what makes this one of the most important units in statistics. And that is also why this video has been so freaking long. I know it's like 40 something minutes. Trust me, I'm tired too. But it does get better from here on out. The next video might also be a little bit long, but after that, it'll get better. So trust me, keep going. Thanks for watching. I hope you learned something. Peace.